So this is 537. This is the sequel to 535. In 535, we looked at basic programming concepts. And one of the last things we looked at in 535 was something called an array. We also looked at two-dimensional arrays. In here, we want to focus on something called data structures, which is really kind of giving a name to something we've already been working with. So a data structure is a structure for holding data. Okay, so what does that mean? Well, when we think about our data, we think of it in terms of variables, doing operations on variables, and storing multiple values for later use under a single variable name. Okay, so when we think about what's built into our languages to begin with, we have our primitive types, which can only hold a value. And then we have our object types, which can hold 0 or more values and potentially do more. It's this object type that we're really going to focus on in here. Even though we've already been focusing on it, we've been building these things. So for instance, in the course right before this, your final project was to build a card game. So we built a card game that had a card object. Okay, so we had a card data structure, and a card object held on to a couple of variables, a suit, a value, and then it probably had a function to display itself, that kind of thing. So we held on to multiple pieces of information and multiple abilities under a single variable name. This has been something that we've been striving for since way, way before object-oriented languages. So when we talk about object-oriented languages, that is languages built around objects like this. It's kind of a chicken or the egg thing. This is a data structure, but it's not the definition of data structures because data structures existed before object-oriented languages existed. So, back to our definition of data structures. A structure for holding data. But it goes a little deeper than that. We can say an object is a structure for holding data. So, all the objects in an object-oriented language are structures for holding data, but not all of them are necessarily data structures. Typically, data structures refers to the common tools for solving higher order problems in computer science. And even that's meant to be somewhat ambiguous. What's a higher order problem? We could just say more complex problems. At this point, we're starting to think about how we solve a problem as opposed to just getting it solved. Because now we're intermediate programmers or something along those lines. Okay? So while a card object is a data structure in that it stores a couple of pieces of information and allows us to do some other things, a card would not be considered one of the grand data structures that belongs to computer science or IT. Okay? That doesn't mean it's not a data structure. Historically, let's kind of talk about where data structures came from. So this is the history of this stuff. Historically, we had variables. And what's a variable? Well, it's a named container for holding a single value. That's really the distinguishing factor for a variable. It can hold a single value. But what if we need to hold more than one value? Well, then we had this thing called an array. A named container for holding one or more values of the same type. Okay, so kind of the evolution of these things. Variables existed first. We need to have a named way of holding a value and remembering it later. This goes back to how human beings solve problems. We remember things, we ask questions, and we use repetition. That's how human beings solve problems. So variables certainly fulfill that, but when we need to store more than one value, variables come up short. So that's where we come up with this idea of an array. But now what's the problem with an array? Arrays allow us to hold collections of similar type of same type data. But what's the weakness of arrays?
It's the memory in a row.
Okay, so that certainly is a weakness, is that it's all the memory must be contiguous. It's not very memory efficient. In terms of the problems that arrays solve, what's a weakness of arrays? Maybe a hint along those lines from the previous class when we did fractions. We had 2 assignments in a row. One of them was to represent your fractions as a 2-bucket integer array. Remember that one? Okay. It worked. We were able to represent fractions that way, but why was that a worse way to represent fractions than our fraction object that we created in the following class? What was the weakness of using 2-bucket arrays to represent the numerator and the denominator? Why were they slow? Okay, that's fractions in general. Oh. Yeah, fractions in general were slow, not because we did them with arrays. We had to remember that the numerator was in bucket 0 and the denominator was in bucket 1. That's only if we're storing 2 pieces of information. What if we're storing 60 pieces of information? We need to remember what piece of information we stored in bucket 0, what piece of information we stored in bucket 5, what piece of information we stored in bucket 32. We didn't have ways of distinguishing between those values, because an array is just a contiguous chunk of memory where bucket 0 holds one value, bucket 1 holds another value, bucket 2 holds another value, so on and so forth. So a weakness of arrays is if we're going to store multiple pieces of information that means something, we do not have a way of remembering that built into the structure. That's where objects are kind of nice. We were able to build a fraction object and give it 2 fields, numerator and denominator. Then we can ask that fraction, give me your numerator, give me your denominator. So we had ways of talking to the fraction in such a way that we were able to know what we were working with, instead of having to remember something was at bucket 0, something was at bucket 1. Okay? So we solved the problem using our object-oriented version of, it's fair to call objects data structures, but it doesn't fall, if you were to get a data structures textbook, you would not find the fraction object as an example of the data structures textbook. We're going to be talking about lots of known data structures like linked lists and stacks and queues and trees in here. But it's still fair to say that our fraction object was a data structure, just like our card object was a data structure. It's just a much more domain-specific data structure as opposed to a generalistic data structure that could be used for solving lots and lots of different problems. So in any case, we needed something better than arrays. Well, before we had object-oriented languages, language like C had a thing called a struct. And a struct let the programmer define one or more named variables for holding multiple pieces of info. So, for example, in C, we could have created a struct that held two pieces of information, a numerator and a denominator. And we could have said that guy is a fraction. Okay? So this predated object-oriented languages. This is not an array. It's kind of array-like, but it's not an array. It's a structure that we can say holds a num and a denom. So I could say f.num or f.denom and put values in there. Okay? So this predated object-oriented languages, and this was called a struct. Object-oriented languages redefine the concept of a struct into things called objects, into a class. The weakness of structs we did not have the ability to use functions or procedures, which now are called methods. So in non-object-oriented language, functions are methods that return a value, procedures are methods that don't return a value. Object-oriented languages, they're all just called methods. Some have a return type of void. So structs were weak in that they could have places for storing a piece of information, but we didn't have a convenient way of referencing reusable chunks of code, abilities, functions, subroutines, procedures, whatever you want to call them. We sort of kind of had a way of faking it in an old language. Not really important for us, but at the very least, it's fair to say it wasn't convenient. So object-oriented languages allow us to create classes that have fields in them, those are our variable names, as well as methods for doing things. Okay? Now, our data structures are going to benefit from that same sort of thing. Now, if we go back historically, let's talk about our first data structure here. Most of today, we're going to be talking about something called a linked list. This is the base data structure that acts as the starting point for most other data structures. So a data structures textbook would usually refer to the linked list. Well, we refer to most of your data structures as being structures built on a linked data type, a linked list data type, and we'll talk about that today. But this is kind of our most generic data structure. Now, data structures, again, existed before object-oriented languages existed. So back when we just had the C programming language, we would have been able to write linked lists. They existed. We could create a linked list. So it's important to draw that line in the sand between a data structure and an object. Okay? Some objects are data structures, but not all data structures are objects. Okay? Although the line is much more blurry today because we can make almost anything, we can call almost anything a data structure if it's a structure for holding data that we're then going to use. But most data structures that we write are very domain specific. We were doing a card game, we wrote a card data structure because it benefited us for the card game. We were writing a fraction homework assignment, so we wrote a fraction data structure because it helped us do fractions. Generic data structures, which the linked list is one of them, this is something that is defined built into most languages, but we don't know that because we're going to write them ourselves and then use our own implementation. Why make it easy, right? Okay, so remember that. When you do your homework, you can't use the built-in linked list data structure. We're writing our own. Once we go to trees, I'll let you use linked lists that are built in. Then we'll just use our own trees. Okay?
As usual.
Yeah, how else would it be fun, right?
Yeah, you bet.
All right, so linked list is a generic data structure that allows us to solve a wide array of different types of problems. Sort of kind of pun intended. So we're going to call linked lists as a competitor to arrays.